network connection. Maybe. So.
It sounds to me, last speaker, it didn't have a very good internet connection. Sounds to me, so be careful. The speaker may need to check in advance. Yeah.
So, Zhang Danyu, you are supposed to be the host for the next session. Can you unmute and maybe say something to test the network?
Can you hear me?
Yes, we can hear you clear, very clear. Okay. So we'll begin in 4 minutes, I believe. Okay.
Okay.
You can start.
Now the meeting will resume. I'd like to invite our next presenter, Jiansong Zhu. The title is Identification of Vortex Boundaries in Three-Dimensional Incompressible Flows Based on the Liutex Shell Interaction. Jiansong Zhu, please begin your presentation.
Okay. Can you hear me?
Yes.
Okay. Can you see the screen?
Oh, yeah, we can.
Okay. Hello, everyone. I'm Jiansong Zhu from Suzhou University in China. I am a first-year graduate student. This is my first time to attend an international conference. I am a little nervous. Please forgive me. The topic of my report is identification of vortex boundaries in three-dimensional incompressible flows based on Liutex shell interaction. This report is divided into three parts: Liutex introduction, observation and analysis, and conclusion. First of all, Liutex introduction is divided into two parts: other vortex identification methods and Liutex vortex identification. Although vorticity is ubiquitous, it has been difficult to give a stricter definition. The first generation of vortex identification method equals vortex and vorticity, resulting in indistinguishable vortex. Therefore, it is obviously inappropriate for the first generation vortex identification method based on vorticity to represent or capture the vortex structure. In the 1980s and 1990s, the second generation of vortex identification methods based on the eigenvalue of the velocity gradient tensor were proposed successively, among which the representative ones are Q, Lambda 2, delta, and Lambda Ci. However, the second generation vortex identification methods also have obvious disadvantages. The vortex should be a vector, while the second generation vortex identification methods are scalar. Therefore, there is the problem of arbitrary selection of threshold value, and it will be polluted by tension, compression, and shear. The second generation vortex identification method cannot accurately identify the vortex structure. In order to overcome the problems existing in the second generation vortex identification method, Liu et al. Proposed a concept of decomposition of vorticity into rotating and non-rotating parts for the first time in 2016, which is called Omega or vortex identification method. However, it still belongs to the second generation vortex identification method, but it is not sensitive to the threshold value and can capture strong and weaker vortices at the same time, which can be said to be the best method in the second generation vortex identification method. In 2017, Chaoqun Liu systematically put forward how to extract rigid body rotation movement part from fluid motion for the first time, and then the rotating part of the vorticity vector. later renamed Liutex vector. Defined as the rigid rotating part of the local fluid motion. The direction is the real eigenvector of the velocity gradient tensor, representing the local rotation axis, the magnitude of which is angular velocity of the rigid rotating. Liutex explicit formula, which was given by Wang et al., is overboard capital R equal to capital R times lowercase r, where capital R equal to omega times lowercase r, means under the square root sine omega multiply lowercase r parentheses squared means 4 times omega c I squared. Number v times lowercase r equal to omega r times lowercase r. Omega equal to number cross product v. Omega times lowercase r is greater than 0, where capital R and omega are the Liutex magnitude and vorticity vector, which lowercase r is the real eigenvector of number v. Omega ci is the imaginary part of the complex eigenvalue of velocity gradient tensor. A special feature of Liutex systems is that vorticity is strictly decomposed into the rotation part, the Liutex vector, capital R, and the residual shear part, capital S. This relationship can be used to study the interaction between fluid and shear in various flows. Next, I will talk about advantages of Liutex method. While Liutex as the third generation vortex identification method greatly outperforms the previous 2 generations, as mainly reflected by one. Liutex vector is an accurate representation of the physical amount of vortex with a clear physical meaning. 2. The vortex identification method represented by Liutex solves the problem of threshold selection for the second generation of vortex identification methods. 3. The Liutex method is able to represent quantitatively the 6 elements of vortex. Okay, the following is the observation and analysis, which is also divided into 2 parts. Liutex shear interaction equation, ISO surface, and slice of Liutex in flow around the 3-dimensional cylinder. In order to study relationship between Liutex and shear, the vorticity transport equation can be used to formulate a governing equation for Liutex in 3-dimensional incompressible flows with a source term depending on the residual shear. The vorticity transport equation for incompressible flow is capital D omega divided capital DT equal to omega times number parentheses times V plus nu times number squared omega. with the Liutex shear decomposition, equal equation can be reformulated as capital DR divided capital DT equal to capital R times number of parentheses times V plus V times number of squared capital R minus capital DS divided capital DT plus capital S times number of parentheses times V plus new number of squared S will be equal to minus capital DS divided capital DT plus capital S times number of parentheses times V plus new number of squared S, where capital DR divided capital DT equal to derivative of R with respect to T plus capital V times number of parentheses times capital R, and V times number of parentheses times capital R equal to the component of the velocity V on the x-axis times parentheses. The partial derivative of the component of R on the x-axis with respect to x plus the component of the velocity V on the y-axis times parentheses. The partial derivative of the component of capital R on the x-axis with respect to y plus the component of the velocity V on the z-axis times parentheses. The partial derivative of the component of capital R on the x-axis with respect to z times I. And so in the above equation, capital V times number of parentheses times S, capital S, capital R times number of parentheses times capital V, capital S times number of parentheses times capital V can be computed similarly. And the new times number of squared parentheses capital R equal to new times parentheses the component of R along the x-axis takes the second derivative with respect to x plus the component of capital R along the x-axis takes the second derivative with respect to y plus the component of R along the x-axis takes the second derivative with respect to z parentheses times I plus new times parentheses
So
component.
you don't need to read every symbol, okay? You don't need to read every symbol.
Oh, 对，that's it. In this way, all terms of equation can be calculated. Which we will call the Liutex shear interaction equation. Here, R and S are Liutex and shear. The term capital R divided capital T is the capital DT is the material derivative of Liutex, while nu times number of squared capital R is the dissipative term and B is the source term, representing the influence of shear on the involution of Liutex. The source term B contains the material derivative of capital S, non-steady term and the dissipative term of shear. Of course, the equation can be formulated the other way around. Combine all Liutex-related terms as the source term, which represents the influence of Liutex on shear. However, in the current study, we will focus on the influence of shear on Liutex, as we are more interested in the dynamics of Liutex. I investigated unsteady flow around a three-dimensional cylinder with Reynolds number of 300. Its computation domain is 12 6. The measure includes 257, 128, 32 grid points in X, Y, and Z direction. The direct numerical simulation, DNS, is used. Immersed boundary method, IBM, was used to simulate the cleaned boundary. Next, we take a look at the slice diagram of Liutex component in the x-axis direction in a three-dimensional cleaned flow. We can see the center of vortex is figure A is from the perspective of XZ, and figure B is from the perspective of XY. Okay. Next, we take a look at the slice diagram of Liutex component in the x-axis direction. In a three-dimensional cleaned flow, we can see the center of the vortex is positive and the boundary is negative. The next graph is a slice of Liutex's component in the y-axis direction. The shading vortex center basically satisfies negative, positive, negative, positive, and the boundary is opposite to the positive and the negative value of the vortex center. Next, we look at the slice diagram of Liutex component in the z-axis direction, which is very similar to the two-dimensional cylinder flow situation. And the shading vortex also shows a regular distribution of negative, positive, negative, positive values. The following is the viscosities slice diagram for the components in the x and y axis. But I can't get any useful conclusions yet. Yes. Next, compared with the distribution of Liutex in the z-axis component in Figure 2C, it can be seen that viscosity has an opposite sign to Liutex in the z-axis component on the vortex boundary recognized by Liutex, maybe indicating that there is a relative strong dissipative effort on the boundary, like a two-dimensional clean water, clean flow. Okay. For the slice plot of the shear in the x-axis component, I observe that the center of the shading vortex is positive and the boundary is negative. According to the slice diagram of the shear component in the y-axis direction, and the boundary of the shading vortex is roughly positive, negative, positive, negative, regular distribution, and then the sign of the internal and the boundary of shear are opposite. Next is the slice diagram of the shear component in the z-axis direction. Compared with figure 2c, the sign of the vortex is roughly the same. By observing Liutex, viscous term shears component along the XYZ axis whose slice location is Z planes in flow around the three-dimensional cylinder. We can conclude that the slice diagram of the components in the Z-axis direction is similar to the two-dimensional case. So next, I will analyze the slice diagram of Liutex source. Liutex source viscous term and material derivative of shears component along the z-axis direction. Separately to see if there are similar conclusions to the flow around the two-dimensional cylinder. Okay, next I compared the viscosity of Liutex source with viscosity and material derivative of shear in the z-axis. It can be observed that Liutex in the z-axis component distribution can see that on the vortex boundary recognized by Liutex. Viscosity in the z-axis component is opposite to the sign of Liutex in the z-axis component. It shows that there is it shows that there may be a strong dissipative effect on the boundary. By comparing the slice diagram of the components of source and the material derivative of shear along the z-axis, source， 这个是对。It can be concluded that the slice diagram are roughly similar in distribution. The source term in the z-axis component is mainly contributed by the term material derivative of shear component in the z-axis direction, while viscosity in the z-axis contributes less, showing figure 5a. Is the slice diagram of Liutex component along the z-axis whose slice location is z planes. The distribution of source term B's component along the z-axis is shown in figure 5b. First, it is clear that the influence of residual shear on the Liutex evolution is concentrated in those shadow vortex areas, outside which the interaction is rather weaker. The term and the material derivative of residual shear and are shown in figures 5c-d. Based on the interaction between mechanism between Liutex and shear, we find that viscosity acts on the vortex boundaries in figure 5c. I thus conjecture that the vortex boundaries can be identified by those high dissipative boundaries. Yes, based on the interaction mechanism between Liutex and shear, we find that viscosity acts on the vortex boundaries in Fig 5C. I thus conjecture that the vortex boundaries can be identified by these high dissipative boundaries.
I apologize for interrupting. Time has 5 minutes left.
Okay, I see. In the following, I try to compare the situation of flow around a two-dimensional cylinder, and we can get the following conclusion. It is revealed that such boundaries exist outside, which the shear has a trivial impact on the involution of Liutex, and inside, which enhancing and weakening efforts of shear on Liutex can be observed. In addition, there is a strong dissipation effort upon Liutex on these boundaries. In the following, I try to compare the situation of flow around a two-dimensional cylinder, and we can get a following conclusion. Liutex is the exact mathematical definition of fluid rotation or vortex, which is the only one that correctly represents fluid rotation or vortex. Okay, I conjecture that vortex boundaries might be identified by these high dissipative boundaries, like the flow around the two-dimensional cylinder. Thanks for your attention. Finally, I would like to invite all of you to attend the international conference on Liutex-based vortex identification methods in Suzhou, China, from August 9 to 11, 20 and 2024. Thank you.
Is there any further questions?
Well, nobody, I would like to ask some questions. You go back to your governing questions. The governing question. Go back to the.
Go back
first,
to the question.
Yeah, go back to. I'm just a little confused. Then you try to explain each term. Go to next. Go to next. Yes. Well, let me see. They here, not only here, everywhere. Yeah. So what it means Rx? What it means Rx? Or what it means Vx?
As Rx is
no, I know your definition. R is Liutex. What is Rx?
Rx is the component of R alone X axis.
Okay, so that means it's R projection in the X direction or components of R, right? Well, then Vx, I think you hear Vx, Vy, Vz is not the U, V, W, but they're all scalar. They shouldn't be vector. So if you look at the Rx vector, you have head, you have vector head. You put the vector there. So we know I is vector. Rx is not vector. Rx is a component, is a number, or is a scalar, not the vector. I think you have similar problem for whole your presentations. Yeah, but we need to know that the R it is vector, but all X is a component. This component is a number, or we say is a scalar. So I think we cannot use this vector to represent the component. So be careful. Anyway, well, you did great job on try to find the source term for Liutex development. Okay, that's my question. Okay, thank you.
Oh, thank you.
Thanks, Jiansong Zhu, for the presentation. Now I'd like to invite our next presenter, Shang Jiang. The title is Liutex and Deep Reinforcement Learning-Based Active Flow Control. Now please begin your presentation. Can you hear me? Shang Jiang, please begin your presentation.
So you should unmute. Unmute. We can't hear you, Jianshang. So maybe we should wait for him. Okay, he came back. Hello?
You need to share screen.
We still can't hear you. Unplug your earphone from your computer. Maybe try that. We still can't hear you. Check your settings of your microphone in your computer. We can see your screen, but we can't hear you. Well, you can make a test. Jiangshan, it seems some noise from you has come out. Speak now.
One way, I think he can save PDF file and send to you. You just give the quick presentation. I think almost 6 minutes passing. He just save his PPT as if too large, you can use the PDF file. But I don't think he already know how to use the, maybe he doesn't know how to use the team or something. So there's an easy way. You just save as a PDF and send the PDF to you. You just help him to read his presentation. I think that's probably the easy way. Yeah.
Okay, I will try that way. Because
I think that's the only way. Yeah, he doesn't know much about how to use the team.
Jiangshan, can you hear us? Send your PowerPoint file to me, maybe through the WeChat, and I will present you work. Okay. So because of the technical problem, I will present the work done by Shangjiang and our. So now you all can see my screen and hear my voice, right?
Yeah, it's clear.
Okay. So the title is Liutex and Deeper Reinforcement Learning based on active flow.
推到你从网页进。哦，也行。
Okay. The names are Jiang Shang and Yu Hongkun. He's a doctor from Tsinghua University and me. Why? So the background is we want to control the vortex state behind the cylinder in a two-dimensional flow, and so we want to combine the machine learning techniques to do this to extract a strategy to actively control the vortex state and make it more, laminar or steady, make it more steady. So so that's the idea, and I believe this is an introduction to the reinforcement learning. Well, so the machine learning world is divided into supervised learning, unsupervised learning, and reinforcement learning, and we are using these techniques to do the flow control. So in reinforcement learning, we have an agent. We are actively interact with the environment through this agent. This agent will take actions, and then the environment will give a reward and a new state to agent. So that's the agent can be viewed as
your screen never change. Your screen never change.
Never change.
Yeah, now change.
Okay. Okay, maybe I should share in the whole screen. Okay. So share whole screen. Okay, so now okay.
Yeah, I change
See the screen. Okay. Screen change. Okay, these are the algorithm behind the reinforcement learning, and I don't want to spend too much time here. The flow, okay, the flow configuration is shown in this figure. The black dot points are sensor points. We can actively collect information. The agent can actively collect information from these points, only these points, not the whole computational domain. I believe in total there are 151 black points, and we are doing the flow control comes from the top and the lower boundary of the cylinder, like in the down right the corner figure, through ejection and suction. So so here are this is a simulation results, and the down figure, the lower figure, should be the control result based on pressure, I believe, based on pressure. That means we extract the pressure information from the 151 points, and we based on this information to do reinforcement learning and get the result in the lower figure. And this work are done by in the reference, and we want to try a second try to do that, to put Liutex, which we believe as the sinews and muscles of the flow, and use that to be the information from the sensor point. So so we are using Liutex as states rather than pressure in the previous reference. And I believe the work is ongoing. So the drag decreases to around about.
Can you help me?
Okay. You have a question?
Can you help me? Oh, Mr. Wall, I come.
Okay, you can now do. Okay, you still have 15 minutes. I'll
Okay,
stop
I will
sharing, and you may continue from the results. I believe people are more
Okay.
interested in the results. Okay.
Okay. Sorry, it's my bad. My topic name is
Hello? We can't hear you.
Okay. Okay. I will start. Hello everyone, my name is Shang Jiang from Suzhou University. My topic name is Liutex and deep reinforcement learning based active flow control.
Shang, you know,
There are
you only have 15 minutes, so maybe you can go all the way to the flow configuration and explain the flow configuration and the results. Okay.
Okay. Here are the flow configuration. The article we mainly refer to is showing below Mr. J. Roboter's artificial neural network trained through deep reinforcement learning discover control strategy for active flow control. The simulated geometry structure is adapted from a well-known benchmark 2D test case. Sharp et al. 1996, consisting of a cylinder with a non-dimensional diameter of d equals to 1 immersed in a box with a total length of L equals to 22d along the x-axis and a height of h equals to 4.1d along the y-axis. The origin of the coordinate system is at the center of the cylinder, which deviates slightly from the center line by 0.05 in the y direction to help trigger vortex shedding. Here are the picture of the flow. Here are 151 points in the channel shown as the black points. Their functions are to read velocity or pressure data from the then it's transformed into the state information and passes it to the agent. At the same time, there are two jets on top and the bottom of the cylinder, one below and another suction. There are action of agent, so we can view the whole cylinder, including two jets, as agent. The Reynolds numbers is said to be 100 and density rho equals to 1. It's just incompressible fluid, and the inlet velocity is set to a parabolic profile, as shown there. Here applied no slip boundary conditions on the top and the bottom of the channel. The mesh is refined around a cylinder and consists of 9,262 triangle elements using finite elements method. The numeric time step is dt equal to 0.005. The computational domain and other boundary conditions are shown there. You can see the picture. We have given agent, state, and action. Just the reward function is left. The instantaneous reward function RT is computed as computed as follows. The signal indicates the sliding average back in time over a duration corresponding to one vortex shedding cycle. Here are their results. For the beginning, the flow generates common vortex rate and the drag coefficients fluctuated periodically around 3.2. So the flow can update. Then put reinforcement learning into the flow control, and it seems to be useful. The drag coefficient has decreased to around 2.95. It has indeed achieved drag reduction, and the flow looks more steadier, like the picture. Due to the strong correlation between Liutex and vortices, our desire is to reduce the impact of vortices. So combining Liutex and reinforcement learning is the way to investigating the flow control. Here is the Liutex explicit formula. There have been shown many times, so I just pass it. On this basis, we want to add Liutex or shear quantity to state information, then use reinforcement learning to train control model. We compute Liutex or shear at 151 points, as shown before, by using the explicit formula. So here are the results and the expectation. The picture is we using Liutex and as a states, then send it to the agent to train the control model. And in the beginning, the drag is about 0.164, and then during the training, the drag is decreased to around 0.159. And it makes some drag reduction. But there are some errors maybe. I think if there are any other information contaminated the date and influence the control strategy. So it's for future research. And my expectation is we want to do more research on flow control by reinforcement learning. First, we can change the props positions to extract different flow information and send it to the agent to learn better control model. The second is combine facility Liutex shear to study which is important information. The third is use different reward function to evaluate the action. The last is to replace TensorForce with PyTorch, because maybe PyTorch is more professional, is more fashionable now. Okay, this is all my representation, my topic. And in the end, welcome to our conference in the next year in Suzhou, China. Welcome everyone. Okay, thanks for listening.
Okay, thank you for your presentation. Now, does anyone have any questions or discussions regarding the presentation? If there are no further questions,
Well, yeah, I just asked some questions. So I know you try to reduce the drag by what kind of tools. I didn't. I'm not very clear. You just put some sensors or how to do the flow control by what? But what kind of tools? Control of you want to control the flow, right? So reduce the drag. So what kind of tool you use? You just use different shaper or different
Ejection.
Oh yeah, you put the ejection
on the
and
top
the
and
suction,
bottom of the cylinder.
suction and ejection, right? Okay. Then you control them. That's
the frequency
active.
Yes.
Active flow control. Okay, but you say your improvement from 1.016 to reduce the 0.15, it is almost no change. I'm a little curious. So what is the
yes
the drag
it
before
may be
and
some
after?
because I use the trained model, so it may be it has been.
Yeah, you say before that you can get like drag something like 0.16, but after your flow
actually,
control,
Professor Liu, actually the main goal is not
Maybe
to
like
reduce
this.
drag. The main goal is not to reduce drag, because the Tacoma bridge, the vortex street creates this force, periodic force, and destroy the bridge. So the main goal of this study, I
Sorry,
believe,
the internet is
not only the reduction of the drag or change the frequency.
The main goal, yes, the frequency and make the flow more steady.
Okay.
So okay, I have a question, Shangjiang. So have you what is this result? What you get and what you didn't get?
I get is the reinforcement learning. It rarely can control the flow, and like the result, the flow is more steady, and what I didn't get is the state I changed, but the control strategy aren't very nice, and it's not for expectation.
Okay, actually, our idea is to replace original information by Liutex, which we thought to be more reflectable of the flow structures. So that's the only the idea behind this work, and it is still ongoing.
That's
Yes.
I think you assume Liutex is more important to the frequencies. Sounds to me say to the frequency change. But this need a further study.
Yes, thanks, Dr. Liu.
It's now time for Sheng Zhang's presentation. The title is Simulation of Droplet Flow in a Buffer Plate, Application of the Liutex and the Liutex Omega Criteria. Please begin your presentation.
Hello, can you hear me?
Yes, we can hear you.
Can you see my screen?
Yeah.
Okay, I'll start. Hello everyone. Today I want to give a presentation about the simulation of wave place. And this is the wave place. It is used to remove water from the airflow. For example, if the airflow enters the tortuous channel from the below, most droplets will hit on the plate and become liquid film and flow down, and then and thereby the dryness of the airflow will increase, and this is what we want. The performance of the well place is generally evaluated by two indicators. The first is the stream water separation efficiency. The second is the pressure drop. The higher the separation efficiency means that this wave place can remove nearly all the water from the airflow. This is a stream generator. It can generate a gas laden with mist, and if the gas go upward, the discrete phase will go down, and this is a wave place. If the flow goes through this wave place, the discrete phase will go down, but the continuous phase will go up and go into the turbine and push the turbine to do work. And why do we need the air to be dry? Because the turbine will have a high working efficiency in a dry environment. Yeah, so it said that if the separation efficiency of this wave place increased by 1%, then the power of the power plant will increase by 0.25%. So a good wave place can bring us the economic benefits. Most simulation about this wave place is based on the Fluent and CFX, this kind of commercial software, but this work is done by OpenFlow. It's open source software, safety software. It will involve lots of different physical phenomena when modeling the two-phase flow. For example, this is the liquid. If and the airflow can blow the liquid into small droplets. Yes, like that. This phenomenon is called entrainment. And in addition, if a droplet hits on the wall, it not necessarily become liquid film. It can also become several smaller droplets. And in addition, we need to consider the two-way coupling between the two phases, because the airflow can apply a drag force on the droplet, and the drag force will maintain the motion of the droplet. And in addition, the counter force of this drag can also produce turbulence to the airflow too. We use the Euler Lagrange method to describe the behavior of this two-phase flow. The continuous phase is controlled by the Reynolds averaged NS equation, and the discrete phase is controlled by the motion equation. And this is the NS equation. This is the gas velocity of the gas, and this is the motion equation of the droplets. This is the drag force coefficient, and this is the velocity of the droplets. And this is the Reynolds. This is the Reynolds stress tensor. In this case, I use two different turbulence models to calculate that. The first is the standard K-Epsilon model. It's very popular and is able to predict the flows in mainstream area well. And the second is the K omega SSD model. It combines the advantages of the K omega model in the near wall vision and the K epsilon model in the free stream. Initially, it only have the continuous phase. When the continuous phase stabilized, I will inject droplets into this computational region. And this is the assumption of the droplets. We consider the two-way coupling between these two phases, and the droplets are considered as hardwares. And this is the geometry we want to compute. It's a two-dimensional wave place. It's a two-dimensional case, and we wanted to create a full hexahedral mesh on this geometry. In addition, our boundary has the boundary layer mesh. The difficulty is that I have to create a boundary layer mesh on this thicknessless face. This thicknessless face is hook blade. So I'll first introduce some basic idea about the SAEM. SAEM, this is the block in SAEM. Block must be hexahedral. So if the blocks fit the geometry very well, then the mesh quality will be very high. To meet our requirement, I'll first add some auxiliary lines to the original geometry. This is the auxiliary line. It is used to associate the vertex of the block to the points of this geometry. With this line, and we use a strategy called burn-up strategy. It means I first create a small block to fill this region, then create a new small block near the previous block to fill this region, and repeat the process until all the region is filled by the blocks. So this is the results. This is geometry. These are blocks, and this is a mesh based on these blocks. You can see all mesh is hexahedral, and our boundary has the boundary layer mesh, and its quality is very well. Most of them is about 0.95. Then we can start calculation, but we still have write the stream water separation efficiency calculation program by ourselves. Initially, I want to design this program as a post-processing program, but then I realized that I couldn't do that. So I start to collecting droplet information during the two-phase flow calculation process. That is mean I need to implement the code in the server. This is the workflow of this program, but I want to explain that it through an example. If M bin is equal to 5, this means I will have 5 bins. This is the first, second, third, 5. The first bin is this range, and then I inject 10 droplets at the inlet. This is the diameter of each droplets, but at the outlet, we just find, for example, 3 droplets. This is the diameter of the 3 droplets, which means 7 of the droplets have been removed by the equipment by the workplace. So its total separation efficiency is about 70. But we still want to know its separation efficiency in each bin. For example, for the first bin, we inject 3 droplets, but we just get 2. So its separation efficiency is 33. And for example, the third bin, in the third bin, we inject 2 droplets, but none of them we find at the outlet, which means all particles has been removed by the equipment. So that's very good. The separation efficiency is 100% then for this bin, and so on. Then we also all those vortex identification methods is based on Galilean invariant. The Q criterion is a very popular criterion. The Liutex criterion represents the pure angular speed, and the omega Liutex criterion is normalized to 0 and 1. Then I want to introduce the result of the discrete phase. The origin point is the experimental data. Let's see, the K omega SST model gives the better results than the K epsilon model, and the dense mesh have a better results. When the diameter is bigger than 10 micron, the separation efficiency is nearly 100%, but is less than 10 micron, it will decrease. Then is the result of the continuous phase. The presence of the hook blade makes the fluid to accelerate strongly, and the acceleration makes the droplets to directly hit on the wall behind the tips. This is what we want. So this is good to the separation. In addition, we can see the K omega model can make the high speed region sharper and more concentrated compared to the K epsilon model. And this blue region is the low speed region, and all this low speed region is recirculation region. If we zoom in, we can see the recirculation clearly. And in these pictures, we can see the influence of the droplets or the discrete phase to the continuous phase. The discrete phase flow with the airflow. Then we can see this the vortex structure. It's clear that omega Liutex gives us a much more detailed vortex structure than the other two. All of them gives the similar outlines of vortex boundary. There are vortex nearly all the corners and behind the tips. We can see. Yeah. Then we can see this is a straight vortex trigger similar structure, and we can see the discrete phase, the influence of the discrete phase to this structure. This is a conclusion. The first conclusion is that the K omega ST model is closer than the experimental data. The second is if the diameter is greater than 10 micron, then the separation efficiency is basically 100%, and this is verified through experiment and simulations. And the smaller the diameter of the droplets, the lower the less than 10 micron, the less the separation efficiency. The third is that the turbulence model have a greater impact on the calculated stream water separation efficiency than the mesh. That is, the denser mesh does not improve the results much. And the different criteria gives similar vortex structure boundary. In this case, Q criteria provides a more symmetrical result compared to Liutex criteria, because it matches omega Liutex criterion more. And the most is the omega Liutex criterion gives the most detailed vortex structure. That's all. Thank you.
Okay, thank you for your presentation. Now, does anyone have some questions or discussions regarding the presentation?
Nobody question? Well, I'm not very familiar with this. I just guess, assume. So you solved airflow with the droplet. Actually, the airflow, it is you use the originally. Now
Yeah,
it's 3
that's
questions,
still
right?
working. That did feel better.
Excuse me.
Can you hear me?
Yes, but I don't.
No, I just say you solve the fluids like airflow separately, which is not considering the droplet, right? Then after you get a flow field, then you try to capture the droplet. You use the droplet equation to separately, right?
I5 is telling you.
Yeah, look at your governing equations. Yeah.
This also has.
It's a two-way coupling.
The first equation is, I think, is something like a Navier-Stokes equation, right? Just like one phase, not two phases.
No, it's two phase. I first.
Yeah, then the first equation. The first equation, I say, well, I cannot see any kind of. Now, this is the second equation. Yeah, that means you solve the fluids, solve the, you call it gas or air. It is used now with 3 equations. That's correct. My understanding is correct. Yeah. And then after you get a flow field, you go back to try to find a UD, something like that, the particle. Well, we know the particle speed is not a fluid speed. That's what it is. Also simplified model. I think it is cannot be, you know, like DNS for the particle moving or something like that. It just solve additional equations for particle. That's my understanding. I'm not sure it's correct or not correct, because this is two-phase flow. I think this not looks like one phase. It's two-phase.
Yes, it's two phase.
How to find the particle?
This curve. This term. In fact, this
this
term is
include
include the drag force.
That's the equation for the particle or drop. It's called drop. That's the equation of droplet, but it doesn't affect the first equation. If we said it's affect where it is, I cannot find it. Yeah, because the first equation just the pure. Now it's three equations. It sounds to me. I know that when you solve the flow field, then you go to the second equation about particles. Yeah, I understand this, but this is also, I think that's the simplified model, I think. The particle cannot follow this kind of, law or this kind of governing equations. This is simplified, I guess, yeah. Because I don't know what's the FD. FD is the function, or I don't know what's the definition. It's FD.
Oh, FD is definitely. I forget to give that. And so nevertheless, is the hardware model for FD.
Yeah, this is a particular for the particle, for particles. Well, but I think the first equation you solved independently, because I didn't find any term in your first two equations. Only thing I don't know it is SV, because it's substrate. But you don't have a definition for SV. If SV is related to UD, then you say it's a couple. But it sounds to me now, the two equations are not a couple, separate. Yes. But you don't give the SV definition. We don't know what SV is. If SV just means for example, just means some body force or something like that, we don't know. But if SV is a function of UD, then you couple. But if SV is independent of UD, it is not coupled. It's independent.
But actually, if S5 didn't include the FD, then why do we have this picture? Yes, this picture means the droplets have impact on the continuous phase.
Well, I didn't say the droplet doesn't affect your flow.
But the droplet is too small, and for the open form is I didn't make it to visualization this droplet, but in fact it has. This include nearly 50,000 droplets. So it's very hard to visualize them one by one.
No, my question is, what is the definition of SV? Now, you may just use open form. It's other people's code. It doesn't have, I'm not sure, It sounds to me you didn't give definition for SV. If we suppose SV is 0, for example, is 0, then that's exactly something like an incompressible flow. Now it's through the questions for incompressible. Sounds to me. If SV is ignored, unless your SV it is related to UD, but I don't have formula for SV. I didn't find it.
Yes, I forget to give
decoupled. Yeah, decoupled. That means you're decoupled to equations.
Yes, I know.
That sounds to me. Yeah, they'll say from your well. But anyway, this is complicated, and also I don't fully understand about your turbulence model. But you say is K omega SST is the best. Is correct?
Yes, this one is better than this one.
Well, the K epsilon model apparently have problem because when you go to the wall, near the wall, epsilon is 0. So K over epsilon is infinity. But really your eddy viscosity, it is 0. But K epsilon will give infinity answer. So of course we cannot use K epsilon model for the near wall area. We cannot. Well, they try to use the K omega combined with the K epsilon. That could, we don't know. Well, I think Dr. Wang's group will give some, explanations. So combine, where combine, how combine. Well, that's maybe the case related. I don't know. So that could be the problem. Yeah.
This model is provided by the open form. Actually,
I know that. I know that. That's by open form. They just the SST's famous model. I know that it's a famous model, but it may not, agree with the physics. The different issue. The different issue. It mean, well, anyway, the model, turbine model is empirical. There's no reason. It's empirical. That's case related, but it shouldn't, against the physics. The physics, it sounds to me, is clear. The physics is clear. When you're near the wall, the flow becomes laminar. That means the eddy viscosity is 0, exact 0. I'm not sure SST can give 0. Physics, we talk about physics. That's near the wall. But we don't have eddy. There's a laminar layer. You don't have eddy. How to get eddy viscosity? So it doesn't make much sense. Yeah, but no matter is K epsilon, K omega, or SST, you cannot answer this question. The question is, it is, near the wall, the eddy is 0. The eddy create the eddy viscosity, it is 0. So turbulence, mu turbulence is 0. I think you use the computational fluid dynamics of the book, right?
Yeah.
It's written by Dr. Tu? TU? No. So that's what it's a computational fluid dynamics. Well, as I said, well, no matter. Well, that's another issue. That's another issue because I just thought, because I have the more time, as I said, I want to discuss this in more details. So yeah, but also the last one, I also don't understand your conclusion. It sounds to me you said omega Liutex is the best, Q is the second, and Liutex is the worst. Sounds to me. Well, I believe this Q and Liutex is related to the threshold. I think you need to adjust the threshold. I believe. For the larger vortex, they possibly give the similar structure, but Liutex omega maybe they can capture both weak and strong vortex. They may give more detail. That could happen, but I don't think your conclusion says Q is better than Liutex. I'm not sure, because it didn't adjust the threshold. Threshold, yeah. If we just the threshold, I believe the results is very similar. Yeah, because you don't use the same threshold. They don't have the same. In general, Liutex should be better because he would treat the share as well at the time. So you may just move into the other speak. Thank you.
Thank you. Thanks, Professor Liu.
Okay, it's now time for Shengbin Yang's presentation. The title is Effect of Blade Tip Slot on the Distribution of Blade Tip Vortices in the Horizontal Axis Wind Turbines. Now please begin your presentation.
Can you hear me?
Yes, we can hear you and see the screen. We can't see your screen now.
Hello everyone, Shenmin Yang, a graduate student at Northeast Agricultural University in China. The topic of my report today is the study of the effect of the blended tip slot or aerodynamic curves at the tip vortex of the wind turbine. I will present my report today in the following 4 areas. With the application of the force energy environmental pollution is become more and more serious, as the exploration of the clean energy is imminent. The clean energy sources that have been scaled up international for the power generation are hydroelectric power, wind power, solar power, bronze power, and gross thermal power. The table shows the percentage of the global power generation capacity accounted for by the 5 major clean energy sources. Among the 5 clean energy sources, hydroelectric has the largest share with the unequal advantage, followed by the wind and the solar. And the second largest clean energy source among the 5 clean energy sources, with the energy has greater potential for development. Wind energy has become one of the mainstream. The decrease of the clean energy development due to its width distribution and easy capture, and as well as the relative materialization of the wind energy technology. The installed capital of the wind power is increased by year, and it is installed capital in China, whether offshore or onshore, or capital or large number. Wind turbine are main divided into Vortex wind turbine and Vortex X wind turbine. And Vortex wind turbine are divided into left tip Vortex X wind turbine and drag tips Vortex X wind turbine, of which Harrier X wind turbine have the highest wind energy coefficient effect occur a large market and have become one of the mainstream model. Although the wind energy coefficient effect of the left turbo vortex wind turbine is lower than that of the Harrier X wind turbine. It has been a track occasion in urban and environment in recent years because of its united wind's direction at the opposite of the air driver. Drag turbine Vortex X wind turbine has the lowest wind energy effect among all wind turbine, but it has a larger output turbine and it is used in many applications such as water lifting for irrigation and mix to hurt. During the operation of the Harrier X wind turbine, tip tower will be generated at the tip of the blade, which will reduce the wind energy compensation if system of the wind turbine and affect the dynamic profiles of the downstream wind turbine at the same time. Therefore, separates the tip vortex of the Harrier X wind turbine will improve the wind energy coefficient effect of the turbine itself, and also improve the wind energy coefficient action of the downstream wind turbine. For limited the polar tip vortex of the Harrier X wind turbine, there are many scholars have studied them. Well, many new models have been proposed, for example, scation surface blended tip ventilator, a press surface blended tip ventilator, flat plate ventilator, elliptic blended tip, and the mass of the used blended tip just to limited the accuracy of the blended tip vortex. These mass are effective in limited the generation of blend tip vortex in Harrier X wind turbine, but will increase the difficulty of blended manufacture as well as increase the energy cost. For this reason, this study proposed a mass to limited the vortex at the tip of the Harrier X wind turbine by operation her and both the leading edge of the tip of the blended and the tip of the band. The high velocity at the tip of the blended when the Harrier X wind turbine is in operation, or rather the airflow at the leading edge of the tip to be injected from the tip of the blended through a paper. This limited the generation of the tip vortex. The function as a segmentic degree of the computation drum, which cost of the stationary demanded and rotation demanded. The unit of the computation demanded is 5 times the demand of the wind turbine from the seat of the wind turbine, and the outlet is 10 times the demand of the wind turbine from the seat of the wind turbine. The unit of the computation demand is the velocity unit, and outlet is the zero process outlet, and the stationary demanded and the rotation demanded use the interface surface for data exchange. The computer demanded and divided by a structure guard as shown. In order to graph the reliable of the number simulation, the computer result of 3 turbulence mount are compared with the example experiment volume after created in independence at time step independence are achieved. It finds that the computer result of the RDDS turbulence mount are close to the experimental volume. Therefore, the RDDS turbulence model is uniform used in the next study. Orthogonal design mass is an effect. The fact at economic experiment design mass which can be united to analyze the result by the minimum number of triangle to find the optimal. If combination and the gradient reduce the computer workload, the demand of the hole, the position of the hole, and the number of the hole in the tip of the left planet can be done as a form factor. 3 orthogonal test without consider the repeated table. Take into account the repeatability according to the type of the orthogonal design. Only 9 tests need to be carried out, which reduce the amount of the calculation and save a lot of time. When the rotation speed of the wind turbine is less than 900 RPM, the power of the both the tip preferred wind turbine and the original with turbine increase with the increase of the rotation speed, and the power of the tip preferred wind turbine increase selected compare with the original with the turbine, and the growth rate of the power is less than 3%. The tip perfection highlighted the effect of the aerodynamic properties of the wind turbine in this rotation speed. When the rotation speed of the wind turbine is 900 RPM, the power of the tip preferred wind turbine and the original wind turbine reached the max value, and the power of the tip preferred wind turbine is increased by 5% compared with that of the original wind turbine. When the rotation speed of the wound turbo is greater than 900 RPM. The power of the burst, the tip operation with the turbo at the opener and turbo decrease with the increase of the rotation speed, but the power of the tip operation wound turbo is above decrease than the power of the original wound turbo. At the increase rate of the power increase significantly, this rotation speed rate of the tip operation has a great impact on the aerodynamic profession of the wind turbine. In conclusion, that power of the wind turbine with tip perforation is increased from 600 RPM to, but the power gain is by a higher speed. The fall line diagram of the location and the path surface of the planet of the orbital model and the open hole model are shown when the rotation speed of the window turbine is 600 RPM. The pressed surface of the planet is in the of the Hansen rate flow and no flow separation occurs. The scation surface surface of the planet has a larger area of the flow separated and shown 10 dc of the speed from the root of the planet to the tip of the planet. This is because the planet root scation airflow has a positive tourism angle relative to the tip scation airflow. The angle of the attract over the planet root scation is large. The planet scation surface called tip pressed gradient, and at the same time, the exact centigrade for the and force drawing the rotation of the wound turbine that in the fall of the fluid allows the separating the direction of the plane. And the following separation compared with the other model, the separation of the open hole blade is small. The separation part is close to the root of the blended, and the separating flow of the separated flow is reduced. This due to the fact that after the opening of the leaf tip, the jet in the hole prevent the flow of the precise side of from flowing across the tip to the station. Set and supervise the flow separation. The flow line diagram of the station and the precise surface of the planet in the orbital model and the open hole model are shown when the rotation speed of the turbine is 900 RPM. The same wind speed. as the rotation speed of the wound turbo increase, the tip speed separation increase on the precise surface of the planet. The separation strength of the scation surface gradually decreases, and sharp or candice dispersion from the root of the plant to drag edge of the plant, and the alpha is no longer separated after crest or creating part. This is due to the fact that alpha technique of the cross section from the root to the tip is getting small and small, and the edge of a track is getting small and small, so that for flow separation no longer occurs in the near the tip.
It sounds to me your
combined with
screen
the-
never changed. Your screen is fixed. We don't know what you talk about. Your screen never changed. Your screen is fixed. Yeah, frozen. It's never changed. You talk a lot. We don't understand what you talk about. Because your screen is frozen. It's never move, never change.
In order to feature was like
Never change. You may need to restart it. Yeah. Your screen never changed. You may need to restart it. You use PPT or use the PDF. I don't know. Yeah. If you PPT, you need to close the PPT, then restart the PPT. That's it. PowerPoint. If you PowerPoint. It's never changed. Yeah, now is changed, but when you use the slideshow, I don't know why. You talk a lot, but I'm not sure how many people understand what you talk about. I don't understand because your screen never changed.
Okay. In order to first visualize the inhibitory tip option of the blended flow separation phenomenon and the formulation and seeding of the separation vortex for cross section of the 20 R 15 point R 80 point R and 1980 point R the blended convection represent the first position of the blended root. The media of the blended and the and the back of the tip. Respect separation phenomenon of the under and the open core are sharp in each section.
It's still fixed. It's still frozen. Yeah, you should change different slide. You cannot use one slide to talk forever. So it's still one slide. It's not moving. because share screen, it should be same in your screen. But now I cannot find that your screens ever changed. Never change. Yeah, they change. To go back, the one more, you go back. Well, you should be able to use the what is it called? Is it called the slideshow? You call the you should click something. Fine, yeah. It's a little change. You don't have enough time, so. But you talk a lot, but we cannot see from your screen. This is another talk. No, your talk.
这个取消这个麦克风，这个应该能听到我。
你看 say 个 hello。
我看它这个共享的话，哦，返回到共享窗口才能复原。
共享
是吧？
share yes。
打开这个估计。Hello, can you hear me?
Yeah,
Yes,
I can
we
hear
do.
you.
Okay.
It's now time for your presentation. The title is Derivation of Unified Fluid Dynamics Equations for Viscous Flows in both rotating and shearing state. Please begin your presentation, 帅成珠.
Okay. Can you see my slides?
Yeah, we can.
Okay. 我都这样翻了这个。Okay. Thank you. Hello, everyone. My name is Zhu Shuaichen. Good morning, good afternoon, good evening. Okay, I'm from Fudan University, Department of Aeronautics and Astronautics, and the title of my speech is Derivation of Unified Fluid Dynamics Equations for Viscous Flows in both rotating and shearing states. And this paper was published in the Journal of Hydrodynamics in September, and I'm the first author, and my supervisor, Xu Hongyi, is the corresponding author. Okay, now I will introduce the outline of my speech. Firstly, I will introduce some background for you, and secondly, the first part is the modified constitutive relation for Newtonian fluids. This is based on symmetric shearing deformation. Okay. The second part is the fluid dynamics equations for two cases. And the third part is some analysis of the added terms based on our DNS data. Okay, let's begin. So we know that in the traditional fluid mechanics, the velocity gradient tensor can be decomposed into two parts, which is called Cauchy-Stokes decomposition. The first part is A, and the second part is B. A is strain rate tensor, which is symmetric, and B is vorticity tensor, which is antisymmetric. Okay, so in the traditional fluid mechanics, A stands for strain rate, which is the deformation of the for 1 point in the flow field, and B is the rotation. So this is the conventional constitutive relation of Newtonian fluids for traditional fluid mechanics. T equals to this one. So T is stress tensor, and A is the symmetric tensor, which is a strain rate tensor. And we know that A contains 2 parts, symmetric shearing and stretching or compressing. So conventionally, people thought that the stress tensor is related to 2 parts. One is shearing and another is stretching or compressing. But by now, no experiment could prove that stretching or compressing can produce stress in fluids. So we proposed that we should subtract this part, stretching, compressing part, or SC for short, SC part, and only symmetric sharing part remains only. So specifically, how to do this? So I will introduce the Liu's new decomposition in the principal coordinate system. So in Liu's paper, he said in the principal coordinate system, the velocity gradient tensor can be composed into 3 or 4 parts. 3 parts are rotation, stretching or compressing, shearing. But for shearing, it can be decomposed into 2 parts, which is SC is symmetric, and SSIM, A is symmetric, so it can be decomposed into 2 symmetric tensors, which is SC and SSIM. SC is stretching or compressing, and SSIM is symmetric shearing. So if we only consider this part, SSIM, we should remove SC. Okay, so we should remove this part. If we remove SC from the traditional constitutive relation, the constitutive relation change to this one, like this. Here, as SSIM replaced A in the traditional one. So the ORG here is stands for original coordinate system, because this decomposition is done in the principal coordinate system. But if we governing equations are written in a coordinate system, it should be a regional one. So we should rotate the coordinate system to the original coordinate system. Okay. So based on the analysis before, we can have the modified constitutive relation. Okay, so we modified the Stokes assumptions. Traditionally, Stokes assumptions includes 3 assumptions. In 19th century, Stokes had 3 assumptions. The first one is the stress tensor is linearly related with the strain rate tensor. And the second one is the fluid property is isotropic. And then the third one is when fluid is stationary, the stress in fluid is the static pressure. And we keep the third assumption not changed. Yeah, so we write this assumption like this like this here, the fourth modified Stokes assumptions. And for the first assumption, the linear relation, we keep the linear relation, but how to describe the linear relation is the core issue. So we change a little. So I will introduce our modified Stokes assumptions. The first one is the stress tensor is symmetric at the scale of fluid particle, which is guaranteed by the satisfaction of fluid angular momentum conservation. This is perfectly proved by many papers and books. So based on the first assumption, we can guess the second and third assumption. The stress tensor is a linear function of symmetric shearing tensor for Newtonian fluids. At the same time, the stress tensor, due to its symmetric nature, is not a function of rotation, stretching, or compressing, and anti-symmetric shearing tensors. So here, the second and third assumptions is corresponding to the first assumption of Stokes' traditional assumptions. So based on the modified constitutive relation, we can derive a new set of fluid dynamics equations for fluid mechanics or fluid dynamics. First of all, we should clarify that we have two cases, because the velocity gradient tensor, this one, it's a third order square matrix. So for this kind of square matrix, there are two cases for its eigenvalues. The first case is that one real and two conjugate complex eigenvalues. Under this case, the rotation exists, so we can also call it rotating state. And we, for simplicity, we can call it OR. O stands for one, R stands for real, OR case. And the second case is that there are three real eigenvalues, TR for short. Under this case, rotation does not exist. So under this case, shear only exists. So we can also call it shearing state. Okay. So first of all, we derive the equations for OR case. For OR case, Liu and his team have the principal coordinate system and its principal decomposition like this. In principal coordinate system, the velocity gradient tensor can be decomposed into 4 parts. But it is in the principal coordinate system. So we should do some operation in the original coordinate system. So we should transform it in from principal one to the original one. So in original coordinate system, the symmetric shearing can be calculated by this formula. The first part, this part, okay, this part is A actually, is A minus SC. So we can get the symmetric shearing. Okay. So in the order to calculate the SC in the original coordinate system, we should multiply the transform matrix Q here. Okay. So if we substitute this one, the symmetric sharing, into the new constitutive relation, we can get the new expression of the stress tensor. Okay, stress tensor F in the original coordinate system. So for the new expression, it includes two parts. The first one is T here. T is exactly the same as the expression of stress tensor in the conventional S equation. And the second part is F add. We can also call it added term or added stress. Anyway, okay, this is the difference between the new stress tensor and the traditional stress tensor. So it is the difference. So we can guess this expression. Okay, the difference plus the conventional one equals to the new one. However, in this expression, Q does not have a specific expression, so we should calculate this specific expression. If we substitute the expression of Q, we can get the final form of the F add like this. Here, the small letter r is the component of unit Liutex vector. Okay, and lambda stands for the eigenvalues. Okay, so we can get the dynamic equations or momentum governing equations like this. Okay, so this part is exactly the NS equations, and the difference between the new equations and the S equations is here, is the added terms. Okay, this is equations for OR case. Now let's move on the case of TR. Actually, for TR case, Liu and his team proposed a decomposition method. Okay, but there was a little problem for of this method. Why? Because in the paper, in Liu's paper, they said the velocity gradient tensor can be expressed like this under a newly defined principal coordinate system. In this system, you can see it's a triangular matrix, but this transformation is not unique. Why? Because for TR case, the velocity gradient tensor has three real eigenvalues, but they are lambda 1, lambda 2, lambda 3. But in this matrix, they can swap their positions. So, for example, this picture, lambda 1 is here. But for another case, maybe here is lambda 2. So this is not unique. So this decomposition is also unique. In order to solve this problem, we proposed a new method like this. So the core issue is how to define stretching. We think the core issue is how to define stretching or compressing under TR case. Why? Because if you have the expression of stretching or compressing, you can easily get the expression of as asymmetric sharing and anti-symmetric sharing, and R. For example, R is 0. And if you get this expression of SC, you can use velocity gradient tensor minus the two parts and gets this one. And as sharing can be decomposed into two parts, it's very easy. So the core issue is how to define stretching or compressing onto TR case. So similarly, we consider the physical meaning of eigenvectors. Because in OR case, when the Liutex exists, the direction of the real eigenvectors, eigenvector of the real eigenvalues is eigenvalue is the direction along which the fluid there's only stretching or compressing deformation. Okay, so this axis is called the rotation axis. So similarly in TR case, there are three eigenvectors. So we think along the three eigenvectors, the fluid only has stretching or compressing deformation. So in a TR case, actually the stretching or compressing tensor includes three parts. One is for lambda 1, one is for lambda 2, and another is for lambda 3. So we abandoned the concept of the principal coordinates for TR case. We define three temporary coordinate system where z-axis is the direction of one of the eigenvectors. For example, for the first eigenvector lambda 1 in this temporary coordinate system, SC is like this. SC1, the first part of SC is like this. It should be noted that this is expressed in the so-called temporary coordinate system. So we should transform it to the original coordinate system. So we do this transformation. Okay. In the original coordinate system, the first part of SC is like this, whereas the small letter s stands for the component of the unit eigenvector. Okay, the first eigenvector. So similarly, we can get the second part and the third part of SC, and we added them together. We can get the total SC like this. Okay. So we successfully get the expression for SC, or stretching or compressing. And after get the expression of SC, we can get the expression of symmetric sharing by this expression. Okay, this is A actually. So similarly, okay, sorry. Okay. Similarly, we substitute the expression of sharing, symmetric sharing into the new constitutive relation. We can get the expression of newly derived stress tensor. Similarly, similar to the OR case, it includes two parts. One is T. T is exactly the same in the S equation, and the difference is F add. Okay, so we can get the similar equations for TR case here. The expression of TR case is exactly the same of with TR OR case, but the expression of F add is different. Okay. So now we get the dynamic dynamics equations for OR and TR case. So we get the complete equations. And you might ask me, there might be some special cases. For example, two eigenvalues might be equal. So if you have this problem, you can see my appendix in my paper. Actually, in the real in the simulation, this case hardly happen. Will not happen. It's not very possible. The possibility is very small. Okay. So after get the new fluid dynamics equation, we should evaluate this term, right? This term, because this is the difference between the NS equation and the new equation. So we use some DNS data to do some elementary analysis of this term. Okay, I will introduce them. Okay, so the data we choose is a channel turbulence, turbulence flow in the channel. The computational domain is like this. There is a main flow direction, and the two one is walls. Okay. So firstly, we can evaluate the distribution for OR case and TR case. So on the left side, you can see a instantaneous picture of the distribution for OR and TR. The black zone is OR and the white part is TR. You can see the distribution of TR and OR is very complex, and generally TR case is smaller than OR case. If we do some statistical analysis, you can see the picture on the right side. Okay, this is the frequency of TR in the along the Z direction, the wall along the direction normal to the wall. So you can see that they are all important. And we also do some comparison between the added terms and the viscous terms. The picture A is the added terms, the magnitude of the added terms, and the picture B is the magnitude of viscous terms. You can see that the magnitude of added term is smaller than that of viscous term, but we can see that it cannot be ignored, although it's very small. Not very small, a little small. So if you do some statistical analysis, you can get this picture. Okay, so we can see that the generally or statistically, the magnitude of the viscous term is about 1/10 of the magnitude of the viscous terms. So we expect that it will have some effect on the results of DNS simulation. And also we can do some analysis for the OR portion and the TR portion. So we can see that for the magnitude of the added term, OR and TR, they both contribute a lot. So they are both important. Okay, that is all my all my speech. So in the future, the effects of the added terms in the dynamics equations can be investigated by direct numerical simulation of the new equations. and this simulation is doing by our by our computer now. So I think in the next month we can get the elementary analysis of our data. Okay, thank you very much. Okay.
Thank you for the presentation. Now, does anyone have some questions or discussions regarding the presentation?
Well, Robert, I have several questions.
Okay.
First one, so your computational results is still old equation.
Yes,
so
yes.
Did you find, well, suppose it is turbulent flow, suppose, and did you ever use new governing equations?
The data in my slides is the old one, but we are doing the new simulation now. Yes, but it takes a lot of time. Okay.
How do you judge the new governing equation and the new results are better than the old one?
I think the NS equation actually can describe the physical phenomena in the nature. Okay, so I think the result of new equations should not be very different from the old one. I think they should be very similar. If they are not similar, I think my newly derived equations are wrong. So I don't know the results.
So there is no judgment, no conclusion. So you don't know where the new equation is better than the old. But we have two different type of problem. One is the laminar flow. You can come. Maybe turbulent flow is more difficult because anyway, you need to use some model. Unless use DNS, where it's hard. And even for laminar flow, you don't have any evidence show the new governing equation is better than the old and the traditional NS equations. But the NS equations already proved to be correct by laminar flow, but it's just the failed for the turbulent flow. So there is no proof says Navier-Stokes equation is failed for the laminar flow. That we don't know, but at least we didn't find it. But you say now you get a new equation, so you can show the people so the new governing equation get better results for the laminar flow, but because turbulent flow is too complicated. I don't think that we can compare. Yeah, you don't have it. Yeah.
Okay. I can explain it. Actually, if because we remove the SC part, okay, that is stretching or compressing part from the original one, the conventional equation. So I think in laminar flow, the new equations is exactly the same with the S equation, because in laminar flow, I think the stretching or compressing deformation is very, very small, right?
Well, it depends on incompressible or compressible flow. So it is hard to say.
Yeah.
But for incompressible flow, it's very small actually. Yeah. Zero. Well, three together is zero. That's trace zero. But for compressible, it's hard. Well, that's just one question. It's a logical question. You have no evidence. Say the new governing equation is better than the traditional. You don't have. But if you have, you should show to the people. Well, that is one question. The second question is you look at back your stretching one, SC1, SC2, SC3. You look back to that. Yeah. So I think that there's some problems there.
Okay.
Yeah, SC1. But you can separate these terms. But next step, you try to use eigenvector. That's the next step. Yeah, then you try to use like this. Well, this system, right? This is I suppose the orthogonal system. So you use that. That's for the number one. You call number one really is number three. So it's okay, but you use S. So you use this one, and well, I think you change the 9. If we put a 9, they are orthogonal. That's one system. You do the rotation. You do the rotation by S. Really, because Q you didn't do that. Then you do the well. You try to get back, right? You try to get back as number 1, but you use the one matrix or use rotation one matrix already. When you do the second one, the different rotation. So you just cannot, use different metrics, to get back to the original. So as all three, lambda 1, lambda 2, lambda 3, you should use the same orthogonal metrics to do the rotation. It sounds to me you use 3 different metrics to do each term, you do the rotation. So this is not, I think is not consistent. So you can look at that. This is one. SC means origin. You rotate it to the origin because lambda 1 is, you can see there's a principle. You look back, there's one matrix. Be careful is that there's one matrix. Suppose you have orthogonal. Then you do the lambda 2, you get another matrix. That means each principle, you go back, use different matrix, not the same matrix. And this is not consistent. That's my opinion is that. Yeah. You how to do SC2. You use another matrix.
Yes.
So S you use 3 matrices to do 3, you call the principal term. So it's supposed you only can use 1. So that's the reason I say is you know that the Chen Xi, Mr. Chen Xi Ma, he used a only one unique metric to do rotation, but apparently used 3 metrics to do the rotation. I believe that's not consistent. So that's the problem with this kind of decomposition, I believe. But I know this because I'm very open to any kind of idea. So that's I said. You already published. I know that you already published, but this is a question. So you really use 3 metrics. Yeah, 3 times, but it's not consistent. The 3 metrics are different, not unique. Not unique. You cannot do that. That's what I say. Yeah. So that's the several problems with your paper. I think. Yeah. But Ma did. I think Ma did. But you can read his talk. I think his opinion is unique. Yeah, and consistent. I think. Well, it can be discussed later, but apparently we have such problems. Okay. Yeah, sorry to give some comments. So.
Okay. Thank you for your suggestions. Thank you. Okay.
Due to time limit, we are need to move on to next talk. It's now time for Ting Zhang's presentation. The title is Numerical Study on Aerodynamic Performance of the Blade Airflow for Wind Turbines during the de-icing process. Please begin your presentation.
Hello, can you hear me?
Yeah, we can hear you and see the screen.
Okay.
Hello everyone, my name is Qin Zhang, and I come from Northeast Agricultural University in China. I'm honored to attend this conference. The topic I'm reporting today is numerical study on aerodynamic performance of the blade airfoil for wind turbines during the ice process. Next, I will report on 4 aspects: background, research content, results, and summary. The first part is the background. As a renewable energy source, wind power has the advantages of environmental, content, and sustainability. Therefore, wind power has been widely used worldwide. According to the data from 2015 to 2020, the cumulative installed capacity of global wind power and the renewable data installed capital of wind power have been increasing year by year. With the continuous development of the wind power industry, a large number of wind farmers are now moving towards high altitude and low temperature areas. In this environment, wind power has encountered a very serious problem, which is the occurrence of ice. When super cold water droplets come to contact with a solid surface, it is known as ice. The harm of ice to wind turbines is significant, including its impact on the agricultural performance of blades. Ice on wind turbines blades can greatly reduce their aerodynamic characteristic, leading to a decrease in wind turbines output power. Ice formation on wind turbines can also increase their overload. After the structural safety of wind turbines and thus reduce their surface life. In addition, when ice falls off the wind turbine's blade, it can also pose a serious threat to nearby personnel. The creating de-icing method mainly includes 3 categories. The first type is mechanical de-icing, which mainly use manual de-icing equipment for de-icing. This method of de-icing has a high labor intensity and a high risk factor. The second type of method is active de-icing. This method mainly includes actively de-icing the blade through heating methods, such as internal heating of the fan, internal electric heating, and external electric heating. This method requires a large amount of heat and the need to be conserved based on comprehensive factors such as system complexity, cost, and heating efficiency, according to actual situation. The third type of method is fast-acting ice, which refers to coating on the surface of wind turbines to use the adhesive of ice to the substrate surface. This method is no cost and widely used, but over time, the anti-icing coating is prone to detachment and failure, and the anti-icing efforts of wind turbine fleets will become worse and worse. This study mainly used the identification results of the Omega method to compare the fluid vortices of ice and clean air force, and explore the influence of ice on the airflow flow field. In this study, French software was used to simulate clean and ice airflows, and the simulation results were identified using the Omega method to investigate the effects of icing on the flow field of the airflow. The sixth part is the research content. Conduct icing experiments using an icing wind tunnel and record the icing process of the airflow using a high-speed camera. Export the images from the camera. Use software to process the ice info image into data. Use modeling software to model and obtain a model of the icing airflow. Import the built model into ICEM software to draw a grid. Then use French software for simulation and process the simulation results using the Omega method. Next, the third part is the results. This is the vortex diagram of the clean airflow and the ice airflow. It can be seen that the vortices are dense in the first half of the clean airflow surface, sparse in the second half, and dense on the entire airflow surface of the ice airflow. This is the vortex variation of creating section of the airflow, which shows that the surface of the ice airflow has more vortices than the clean airflow, and the tail vortices have more vortices, which are more complex. This is the vortex diagram of the suction side of the clean airflow and the ice airflow. It can be seen that compared to the ice airflow, the vortex distribution on the lead edge surface of the clean airflow is more uniform. Compared with clean airflows, the vortex in the late half of an ice airflow increase, and the changes in vortex become more complex. This is the vortex plot on the pressure side of clean airflows and the ice airflow, compared with the vortex plot on the suction side. The vortex in the late half of the airflow is less. From the vortex plot on the pressure side, it can be seen that the vortex become too detached from the airflow, resulting in less vortex on the surface of both airflows. This is the front view of the vortex mass for clean and ice airflows. It is evident from the figure that the vortex on the surface of the frozen airflow increases significantly compared to the clean airflow, and the vortex in the wake of the airflow increases, resulting in more complex changes in vortex. The last part is a summary. In this study, The ohmic method was used to identify vortices in the flow field of ice and clean air force. The research shows that icing has a significant impact on the flow field around the air force, and the distribution of vortices at the icing point is uneven due to the impact of icing on the flow field of the air force. The vortices in the later half of the surface of the ice air force increases. The number of vortices on the surface of an ice air force increasing compared to a clean air force, and the vortex changes in the wake of the air force are more complex than the surface. My report ends here. Thank you very much for listening.
Thank you for the presentation. Now, does anyone have any questions or discussions regarding the presentation?
Okay, can I ask a question?
Of course you can. Welcome. Yeah.
Thank you very much. I'd like to ask a question regarding the evolution of the ice on the surface. What kind of model did you use for the ice formation and the growth on the surface of the airfoil? And that is the first question. And the second question is that what kind of humidity you included? You assumed in the free stream in your computation.
The session chair should help let the author to answer the question. So where is the author or the presenter? So the presenter should answer the question. So you understand the session chairman? I don't know who is the session chair, but you should ask the author to answer the question. But sounds to me the author already left. Is it correct? Still here? Zhang Ting is here?
Yes.
Well, yeah, he asked a question you needed to answer.
My humidity is 70%.
Now, his first question is, he asked what kind of model you use. I believe what he said is what kind of turbine model you use. I believe he wants to say is what kind of turbine model you use. But I guess you may just use the commercial software, right? Answers, right? Fluent is correct, my understanding. Yeah.
Yes.
Is correct? Yeah.
Yeah. I use R is
your own
RE.
code. Your own code. Okay. Do you have a turbine model? Suppose you're not DNS, or you do LDS. If you do LDS, for example, do you have a subgrid model or no model? So that's his question. What kind of model is?
No model.
My question, ice formation, regarding ice formation, how the water becomes ice, solid ice is produced on the surface in your computation.
The cold water droplets come to contact with the solid surface. It is known as icing.
Okay. Thank you very much.
I believe they just use different shape. They didn't study the process, how water becomes ice. So that's the ice could be different shape. They just fix the shape, run the program again, and to see is from from what I see is the a lot of water structure, behind the iced airfoil. For the clean airfoil, the water structure is much simpler. And for the iced, that's for my observation. They have a lot of different structures, after ice, because the surface is not smooth anymore. So there could be a lot of, blockage, something or roughness, something like that. So they only treated the shape. They didn't consider the temperature. They didn't consider about the phase transfer from liquid to the solid. I don't think they did that. I don't know. That's my understanding. I'm not sure. I cannot represent them. So I just curious, what kind of software you use? You say your own code or a commercial code? I asked the presenter, the author. I said, which software you use? He didn't answer. Yeah. Well, but anyway, yeah. No, I just asking what kind of software you use. Is
it ANSYS fluent?
Is fluent.
Yes, I use Fluent software.
That's what I said. So fluent, maybe they already have some kind of models there. Well, I don't know. Well, the model is talk about turbulent model or subgrid model. It's not about the water become ice model. I don't think that too difficult and maybe too deep, I think. Okay. And how many grids you use? How many grids? Like 1 million or 2 million or 10 million?
10 million.
10 million. 10 million
Yes.
grid points. It's unstructured structure. It looks like it's unstructured grids, right? Unstructured. It sounds to me.
Unstructured.
Is structured grids or unstructured grids?
I use unstructured grid.
Yeah, unstructured.
Yes.
Okay. Okay. Well, before, the session chair should say, before, we end today's, all sessions, I want to, Dr. Wang, I'm not sure Dr. Lee's here, and if he, I think it's here. So we have some short discussions we need. Is Dr. Lee's here? Is Lee's not here, right? Dr. Lee?
I don't think so.
Well, maybe just Dr. Wang and Yifi and I, and me. So we may have short discussion about tomorrow and after tomorrow. So then, not me. So Dr. Wang should. You have any more announcement, or you just end the session?
Well, we will have continue have the conference tomorrow, right? So
yes.
So I have nothing else to add. Okay.
So we just ended all session. for today, right? Yeah.
Yes. Yes.
So we continue tomorrow at 5 p.m. Pacific time, same time. Yeah. Okay, just like today. Yeah. Well, then maybe Dr. Wang if we need it, but Dr. Ni is not here, so we are short discussion about that. Okay.
Okay.
Well, thank you for everyone and the speakers and the session chair and every presenters. Okay, so we see you tomorrow.
Bye.
Bye bye. Yeah. Let me shoot my. We didn't know each other, so yes. Bye bye. Good night. No, good night. Yeah. It's a good night. Yeah, but well, it is in the China. It's good evening. See, it's good evening. It's almost what time?